Hey everyone, welcome back to day two of the hypothesis testing. Last time, what we saw was a run through of the entire hypothesis test process. So we saw the whole thing kind of happen at once. There was a lot of information to go through and pick apart. And so what we're going to do today is we're just going to focus in on certain parts of the hypothesis test and talk about those in a little bit more detail, and then we'll run through the whole process again. This time seeing what we call a two-tailed test, which is a little bit different than what we saw on the first day. Okay, so again, just remember the big idea here is that we are now testing claims. The confidence intervals estimated, the sampling distributions and normal CDFs and all that stuff, calculated probabilities for us. What we're doing is we are actually testing claims that people make about certain things, about different population parameters. Okay, so the part that we're going to focus in on today is going to be the hypotheses. The very first thing that we do when we set up the null and the alternate hypothesis at the beginning of the test. Okay, it's the first thing that we do. It's how the test begins. We set up these two hypotheses. Okay, so the null hypothesis is usually a statement about the population. It's like an assumption about the population. So, for instance, someone might assume that the mean height of men in America is 70 inches, right? So, this is an assumption about the population. Um, and then we come up with what we call an alternative hypothesis. It's like the contradictory claim. So if I have a null hypothesis that says that the mean height is 70 inches, an alternate hypothesis might be that it's not 70 inches, right? So you have these two competing hypotheses that you are testing. And so the null hypothesis is an assumption about the population. The alternative is usually a contradictory statement to that null hypothesis. Okay, that's why we need two of them. We can't just go with one. Right. So the possible setups for something like this, right? So we have this null and this alternate hypothesis. Uh, when we set up our null hypothesis, we usually put the assumption about the population in the null hypothesis. So that'll go over here. And we can set that up in three different ways. We can say that something is equal to something, we can say that it's greater than or equal to, or we can say that it's less than or equal to. Okay. So when we say that something is equal to, so for example, again, if I assume that the mean height of men is 70 inches, the contradictory statement to that would have to go in my alternate hypothesis. Okay. So, and I have options for how I can set that up. So if I say something is equal to something, then the contradictory statement could be that it's not equal to, or that it's greater than, or even that it's less than. Those would all be contradictory to the idea that something is equal. Okay. If I have a null hypothesis that specifically says something is greater than or equal to, then my contradictory statement would be that it's strictly less than. Okay. And then obviously for less than or equal to, so if my null hypothesis or my assumption about the population is going to be that it's less than or equal to, then the contradictory statement would be that it's more than. Okay. Strictly more than. All right. And that's one of the other things to note is that equality or any statement of equality about the population has to go in the null hypothesis. It cannot go in the alternate hypothesis. All right. So equality never goes over here. It has to go in the null. All right. So make sure you're careful with that. When you do set up your null and your alternate, equality goes in the null. No equality can be in the alternate. All right. Why that is, we'll talk about that based on the outcomes of the test. All right. So when we do run our tests at the very end of the test, we gather our data, we do our collections, and then we have to make a determination about what is true and what's not true. And really, we only have two possible outcomes to the test. The first outcome is that we reject the null hypothesis. And if we reject the null hypothesis, then we are accepting that the alternative hypothesis is true. Okay, so we can reject the null, which means we accept the alternative. All right, so if I reject that the mean height of men is 70 inches, then I'm accepting that the mean height is something different than 70 inches, right? The other option at the end of the test is to fail to reject the null hypothesis. Okay, so we have run the test, we've gathered our data, and there just wasn't enough evidence there for us to reject whatever the assumption was about the population. We can't reject it. Okay, it doesn't mean that we prove the null hypothesis right. It doesn't mean that the actual mean height of men is 70 inches. It just means we don't have enough information to say that it isn't. Okay, and another way to think about that, I know that's kind of confusing, is to think about a court of law, right? When you get arrested, right? I hope none of you ever do, but if you were to be arrested for a crime, you go to court and you get judged by a jury of your peers, all right? But when you step into that courtroom in America, we assume that you are innocent until proven guilty. All right, so we assume innocence. That is our population assumption, is that you are innocent. We have to gather enough evidence to determine that you are guilty. Okay. Now, at the end of the court trial, once we've examined all of the evidence, there's only two outcomes. You are either guilty or not guilty. We don't ever prove innocence. No one ever walks out of a courtroom with the jury saying, "Hey, guess what? You're innocent. We have proved that you are innocent." We never say that. We always say you are either guilty or not guilty. All right. That's one of the reasons why we can never put equality in the alternative hypothesis, because if we reject the null in that situation with the courtroom, if I reject the notion that you are innocent, then I'm accepting that you must be guilty. All right. The second option there would be to say, well, I don't have enough evidence to say that you are guilty, so I can't reject the idea that you're innocent. I'm not saying you are innocent, I just don't have enough evidence to prove that you're not. Okay, enough of that. If you need to rewind that, listen to that a couple of times. I know that there's a lot of logic stuff that goes on in there, and students tend to trip themselves up with that quite a bit. But just make sure you review these things with the notes, and I would watch that over a couple of times. There's also some other great videos on YouTube if you talk about null and alternate hypothesis in there. There's some great videos on there that might explain it from different perspectives to help you gain a deeper understanding of the outcomes of the test. Okay. All right. Also, in the last video, we talked about, or I had promised that we would talk about this left tail, right tail, two tail thing, and we had made some notes in the previous video about when it was left tail or right tail and two tail. Okay, so I'm going to talk about that briefly here to kind of give you some insight. So consider this null and alternate hypothesis. Null hypothesis being that the proportion is equal to 0.5. The alternate being that it is greater than 0.5. So at some point in the test, we're going to be drawing a normal curve, okay, to establish a probability. And there's going to be this expected value in the middle, and we're saying that that is 0.5, right? That was our population assumption. So what we're ultimately going to be trying to find is some value that goes off to the right, because we want it to be greater than 0.5. There's going to be some value over here, and the probability that we calculate is going to be in this tail over here. So when it's greater than, it puts the tail on the right hand side when we calculate that probability. That means that this is a right tail test. And that's what they're referring to with this kind of test, all right, when they say left tail, right tail. So conversely, if we do something that is less than, right, so in this case, we have a normal curve with our expected value of 0.5 here, and our alternate is that it's less than, then we're going to be looking over here on the left-hand side and saying, okay, well, what's the probability of getting this far to the left or more, right? So our tail is going to be on the left-hand side. So this is what we call a left tail test. All right. Then this last one, you'll notice in the alternate hypothesis, this one says simply not equal to, right? Equal to, not equal to, which means that when I'm doing this test and I draw my normal curve, and we have our expected value of 0.5, It means that to prove that something is different than 0.5, I could go to the left or to the right, right? So if I go too far to the left, then we're different from 0.5, right? So there could be a value over here where we say, okay, we've gone too far to the left. Now I don't believe it's 0.5 anymore. Or I could go too far to the right and again, stop believing that it's 0.5. So it creates two tails, right? So we have a tail on each side, and we would want to get the area underneath the curve in both of those tails for our probability or for our p-value. Okay, so this is a two-tail test. And we're going to get to see one of those at the end of the notes today. Okay, so when it's not equal to, we have a two-tail test because we can go too far in either direction. When it's a left-tail test, it's corresponding to an inequality that says less than because we're looking to go to the left. And same thing with the right-tail test, we're looking to go to the right because it's greater than our expected value. All right, so let's look at some examples, all right? Just setting up the null and the alternate hypothesis. So we have a magazine article that claims the GPA of American college students is 2.0. We suspect that it might be different from 2.0. All right, so the magazine is making an assumption or a claim about the GPA of American college students, and the assumption is that it is 2.0. So we're talking about a mean here. A GPA is a grade point average, right? Average being another word for mean. So we're going to say that the mean or the assumed mean of American college students is 2.0. We suspect that it might be different, and notice the use of the word here, different. It doesn't say less than, doesn't say greater than. It specifically says different. Okay, so in other words, our contradictory statement to the assumption here is going to be that the mean is simply not equal to 2.0. I don't know if it's less than or greater than. I don't think it's going to be 2.0. All right, so that's my alternate hypothesis. All right, and because there's a not equal to sign in the alternate hypothesis, this will be a two-tail test. Because if I go too far to the left of 2.0 or too far to the right of 2.0, we could say it's different. This is a two-tail test. Right? Then this one, we have a medical company that claims that its weight loss drug helped its users lose an average of 20 pounds or more. Right? So the assumption is that if you take this drug, you'll lose 20 pounds or more. All right, so that is the assumption. So I'm going to say the mean weight loss, right? We'll just use a symbol for mean here. And we're not going to say equals 20 pounds because if you notice the wording, it says 20 pounds or more. So we're going to say greater than or equal to 20 pounds. Notice that I put my equal to in the null hypothesis, right? So the contradictory statement to that, right, is our suspicion that they are lying and that it's actually less than 20 pounds. So I'm going to say the alternate hypothesis here is going to be less than 20. Notice that I did not say equal to. There can be no equality in the alternate hypothesis. Since it's a less than statement, this is going to be a left tail test. All right, last one here. A certain statistics teacher claims that the average time spent on homework per week is 60 minutes or less. Okay, so there is our assumption about the population. It's 60 minutes or less. So I'm going to say the average time is less than or equal to 60. That is what the statistics teacher is assuming about the population. The students disagree, right? And they suspect that it takes longer to complete the homework. So their alternate hypothesis, their contradictory statement is that it's going to be greater than 60, strictly greater with no equal to in that alternate hypothesis. And this would turn into a right tail test. Okay, so there we go. Those are three examples there of setting up a null and an alternate hypothesis and determining whether or not we have a left tail, right tail, or two tail hypothesis test. All right. Well, let's go to the next page. We're actually going to run through the process of the hypothesis tests again and make sure that we know how to do this. And this is going to be a two-tail test. So this one's going to be a little bit different than the ones that we did yesterday. Okay. So let's start off with reading the problem and we'll set up our null and alternate hypothesis here. So it says a political candidate claims to have 70% of the popular vote. Right, so that sounds a lot like a population assumption there or assumption about the population. So I'm going to go ahead and just set up my null hypothesis right away after reading that. So the null hypothesis is that the proportion of votes this candidate thinks he has is 0.7. Okay, so we're looking for an alternate hypothesis on this one, right? So it's going to be contradictory to the idea that it's equal, right? So an independent agency conducts a simple random sample of 250 voters, and 163 voters indicate they will vote for this candidate. Is there evidence at a 5% level of significance, that tells us something, that the proportion of all voters is different than 70%? So notice, again, the use of the word different doesn't say less than or greater than, it just says simply different than 70%. So our alternate hypothesis here is going to be that the proportion is not equal to 0.7. And because of that not equal statement, we see a two-tail test. Okay. All right. Now, we know at some point we need to use the normal distribution, so I just want to make sure that we establish that we can use the normal distribution. So if you read the information about the data they collected, the sample size was 250, which is great. That's a nice big sample size. And we had 163 successes, which means we are going to have 87 failures. Both of those are bigger than 10, okay? That's what we need, at least 10 successes, at least 10 failures for the sampling distribution to normalize. So we can go ahead and deem this normal, and we will be able to use the normal distribution later on for our probability, okay? All right, so now we want to quantify the variability. This is where we calculate the standard deviation using the p times 1 minus p formula for sampling distributions of proportions. All right, so we use the assumed population parameter of 0.7 for that. So we're going to say 0.7 times 1 minus p, which would be 1 minus 0.7, so that's 0.3. We divide that by the sample size, which is 250 for this problem, and then we square root that. Okay? If you do that correctly in your calculator, you should get a standard deviation of 0.029. Okay? That is what a standard deviation is for the distribution that we are using. Okay, now we want to calculate the standardized test statistic. We want to determine how many standard deviations from the expected value our sample is. Okay, so we're gonna take what our sample statistic was, and we're gonna subtract it from the expected value. So I got to figure out what p hat is, and to do that, I just have to take 163 and divide it by 250. And when we do that, I got 0.652. Okay. Now I like, again, just take a second and pause here. Our sample showed us 0.652. We were assuming that it was going to be 0.7. It doesn't seem like it's too far off. We'll have to see what happens here, but it's not looking good for being able to reject. Okay, so I'm going to go ahead and subtract that 0.652 from 0.7, right? This is the distance between what we got and what we expected to get. And then we divide that by 0.029. That's our standard deviation. And the result here is negative 1.655. So we ended up 1.65 standard deviations to the left. Is that far enough away to determine that the proportion is different than 0.7? We're going to find out. That all depends on the probability. Okay. Now this is where the two-tailed test can get a little confusing. Okay. So when I draw my distribution, remember our level of significance was 0.05. Okay. So whatever p-value that we calculate here, whatever that is, it has to be less than 0.05. And what that means for our tails is that the most area that we can have in the two tails that we're going to be using here is 5%. So I have to split it up. So 0.025 can be over here, and 0.025 can be over here. All right. So whatever these boundaries are, right, those are the boundaries that I need to get. Now, what we got was negative 1.65. All right, so here's 0. And we went negative 1.655 to the left. So it was actually somewhere here. Okay. And to get 0.025 in our tail, we would have had to have gone 1.96, right? This would have to be a negative 1.96. So this didn't go far enough to the left into that tail to make that happen, all right? So we actually went 1.655 standard deviations to the left. We would have to replicate that tail over here on the right-hand side at positive 1.655, and we have to calculate the area in both of those tails. So the way that I'm going to do that is I'm going to say, well, normal CDF, and I'm going to use a negative 1E99, comma 1.6, negative 1.655, comma 0, comma 1. Okay, that's going to give me the area in this left tail created by the boundary that I found here, right? So I'm going to go to my calculator. I'll turn on. There we go. And I'm going to run a normal CDF. My negative 1E99 in there, my negative 1.655, 0.1, and there's our area 0.049, let's say. 0.049, that is the area in this left tail. You can see that area in the left tail, 0.049, is bigger than the 0.025 we said we needed to get, okay? And we're going to have that same area over here in the right-hand tail as well. So we actually have to take this 0.049 and multiply it by 2 to get the total area in both tails. So if I come back over here and I just multiply this by 2, I get 0.098. Okay, that's the area in both tails. This is our p-value. Okay, and then I compare that p-value to my significance level. 0.098 is greater than 0.05. To reject the null hypothesis, we need it to be less than. So this 1.655 to the left, it wasn't far enough to the left. It wasn't far enough away from the expected value to reject the original claim. All right. So our conclusion in context would be that there is not sufficient evidence. To reject the claim. That the candidate has 70% popular vote. Okay? Just didn't get far enough away. I know the two-tailed test can be a little bit confusing. What I always do with the two-tailed test is I always kind of establish that I take that level of significance and I split it up between two tails, and I look at this area over here, this 0.025. That's the area that I would have needed in that left tail for this test. But when I ran my normal CDF on that left tail only, I got a 0.049. That was bigger than the 0.025 in that left tail, which tells me that, you know, it's not rare enough. It's not a small enough probability. But technically what we're doing is we're looking at the cumulative area in both tails, which is why we multiply by 2 to get the total p-value. Then we compare that to the 0.05, which is the cumulative area that we're allowed to have in both of those tails. Okay. So let's just run through the vocabulary stuff real quick. The point estimate, uh, we got that from the data that we collected. So we had 163 out of 250 people say that they were going to vote for the candidate. So that is our point estimate that we use for this thing. And we got 0.652 for that. The population claim, or the assumption that the candidate made, was 0.7, which means our alternate hypothesis has to be the contradictory statement to that. And based on the wording in the problem, they wanted it to just be different from 0.7, so we used a not equal to sign there. Okay, the standard deviation of the statistic, that's where we do the p times 1 minus p, and what we got there was 0.029. The standard, I can't say this enough, this tells you how many standard deviations away from the expected value you are. Okay, and we were 1.655 standard deviations to the left of what we expected to get, which unfortunately was not far enough away to reject the claim. Okay, so when we calculated our p-value, we got 0.099 or 0.098, and our level of significance was 0.05. We want that p-value to be less than the level of significance if we're going to be able to reject the claim. Okay, so there you go. That's day 2. Again, watch it through, go back and rewind to the parts that you thought were confusing, listen to it a couple of times. If you have questions, make sure you contact me. I know this stuff is confusing, but contact me and we can set up a time to talk about it, and I can answer specific questions for you. All right, guys, have a great day.